Thanks a lot. So first of all, I would like really to thank the organizers for inviting me and also for giving me the possibility to swap with Benedetta, and thank Benedetta for your availability. So I'm very glad to be here in person in a better shape, and I would love to discuss with many of you. If you like, we can go outside. So the aim of this talk is really to try to understand something about the properties of the first stars and the first galaxies by doing a journey from the near to far field cosmology. And in particular, I will try to understand and interpret the chemical signature left by the first stars in present-day second-generation stars, so the near-field cosmology, which have been also discussed yesterday, and then in more distant gas clouds, and finally in the galaxies seen by the James Webb. So we already heard yesterday that one of the key properties we would like to know about the first stars is their unknown initial mass function. So I want to stress that we don't know what is the mass range. If there is a peak, what is the shape of this IMF? And it's quite funny, as Alex was already mentioning yesterday, that the most robust constraints that we do have so far are coming from non-detection of zero metallicity stars in ultra-faint dwarf galaxies. And these allow us to put a limit on the minimum mass or on the peak of the IMF. So I want to stress here also that there is a degeneracy. Now, if we have to deal with the chemical signature left by the first supernovae, then unfortunately we have another complication. And the point is that stellar evolution models are telling us that first stars with masses between 10 and 100 solar can evolve with a variety of energy as supernovae, okay? And as low energy faint supernovae and more energetic hypernovae. And yesterday, Alex was mentioning that now there have been a collection of new observations showing that there are many so-called second-generation stars which have an abundance pattern that is consistent with the chemical yields from low-energy faint supernovae. We have really many of these stars. And recently, 2 stars consistent with an imprint from monoenergetic hypernovae have been found. So this implies that there is also another unknown that we need to understand. And this is always neglected, and that is the energy distribution function of the first supernovae. Now, Alex was saying that these low-energy faint supernovae are typically associated to the carbon-enhanced metal-poor stars that we observe today. So why is like that? So to understand this, we can take a very simple model, and I mentioned this one, it was the first one developed 10 years ago by Cook and Piero Madao. And it's a model for the POP3 enrichment of mini halos, and it used the yields from Hager and Woolsey 2010. So on the left, you can see what is the predicted abundance pattern produced by the first POP3 supernovae with different energy, from the low, the cyan, to the more energetic, the red. And you can clearly see that the low energy supernovae produce large amount of carbon, nitrogen, and oxygen with respect to the iron. And this is average over an IMF that is flat between 10 and 100 solar. And on the right, you can see how this first supernovae contaminates the gas, okay, in the carbon over iron with respect to the iron abundance range. So clearly, only these low energy faint supernovae can produce very high carbon over iron ratio at very low iron abundances, while the hypernovae essentially produce, let's say, imprint the gas with much higher iron abundance. Now, if you want to understand why we only observe 2 hypernovae, while we observe many of these carbon-enhanced stars, we can still use a very simple model, but we should complicate it a bit by accounting for the subsequent formation of POP2 stars. And we already saw yesterday that simulations are showing us that the transition from POP2 to POP2 is very quick, and this is also what we found in semi-analytical models. So essentially, these are very simple and general parametric studies, which is using the unknown star formation efficiency dilution factor and exploring the full parameter range, also accounting for the subsequent contribution of population 2 stars. And here I'm showing, again, the carbon over iron with respect to the iron abundances, how the gas is imprinted by the first stars, the first supernovae, and the 100% contribution by the first supernovae is the yellow, and the subsequent imprint by normal population 2 stars. and from left to right, the energy of these POP3 supernovae increases. So we can clearly see that for 100% contribution from POP3, we find the same results by Cook and Madao. And when POP2 stars start to contribute, even with only a 10% contribution, you can see that this carbon over iron shrinks. And then when the POP2 are equal to the POP3 contribution in terms of metal, you can see that essentially you cannot anymore differentiate among the different models. So then we can infer two things. First of all, that the most carbon-enhanced metal pool stars should be second-generation stars, only imprinted by POP3 supernovae. And the second one, and so somehow is easy. I know Alex said it's not easy in reality, but it's easier to find them because we just had to look hard to find the most iron pool stars and then to detect the carbon. While to find these hypernovae is much more complicated because they reside in a space in which you are dominated by the imprint of population 2 stars. And what I found interesting is that these results coming from a very simple and general model are also confirmed by more complicated semi-analytical models coupled with n-body simulations. And this is shown in the right panel here. Here we are using the semi-analytical code Nefertiti coupled with n-body simulations. And what I'm showing here is the distribution of present-day stars that are residing in the galactic halo. And here they are colored depending on the contribution of POP3 supernovae to their total amount of metals. So red here means second-generation stars. So you can see that, again, all the carbon-enhanced, extremely carbon-enhanced stars are second-generation stars. And you can see that we also predict second-generation stars here, and these are stars imprinted by hypernova and also by per-instability supernovae. And I will come back to this point later. Now, yesterday, if I correctly understood, one of the questions was why there are so many carbon-enhanced stars in ultra-faint dwarf galaxies. Now, ultra-faint dwarf galaxies have been already discussed. They are very interesting galaxies. They represent the most metal poor, the most pristine, and the simplest galaxies known, with a star formation history consistent with forming more than 80% of the stars during the first billion years. And already 20 years ago, Nick and Massimo Ricotti produced this very nice work and show with their simulations, that by the way stopped at redshift 9, that the newly discovered ultra-faint dwarf galaxies with luminosity lower than 10 to the 5 were consistent with the results of their simulation, and they predicted them to be the so-called pre-ionization fossils, so mini halos that form their star before reionization. And then 3 years later, Ivan Kirby started to observe individual stars in these ultra-faint dwarf galaxies, producing the so-called metallicity distribution function. And I and Andrea, who was a PhD student at that time, jumped into this business and studied the origin of these ultra-faint dwarf galaxies from a cosmological perspective using a semi-analytical model. And indeed, we confirmed the results by Nick and Massimo. And so we were also finding that in order to produce these ultra-faint dwarf galaxies, we have to account for the star formation in low mass mini halos. And we were predicting this galaxy to have a mass of the order of 10 to the 7, 10 to the 7.5 in terms of total stellar mass. And then naturally, we were also able to reproduce the metallicity distribution function of this object and of more distant dwarf spheroids. Now, this field now increased. We have so many observations, and there are really a huge number of new data available with all the different chemical abundances for the stars. So under the hypothesis that these ultra-faint dwarf galaxies are indeed mini halos, we can, sorry, I don't know what happened, we can build up sophisticated chemical evolution models and study all the different chemical elements and also the role of population 3 stars in these small objects. And here, the stars represent the data, and the contour plots represent the results from these models. Now, the question is, why there are so many carbon-enhanced stars in ultra-faint dwarf galaxies? One can ask this question. What is the fraction of metals injected by different POP3 supernovae which are retained in these small systems? And the answer is in this plot here. And as you can see, we find that the higher is the explosion energy of these supernovae, the lower is the percentage of metals that are retained inside these ultra-faint dwarfs. and essentially for per-instability supernovae, the percentage is less than 0.1%. So this is not surprising. Under the hypothesis that these ultra-faint dwarf galaxies are mini-halo, they have a very low potential well. So this is simply, let's say, confirming pioneering simulation by Volker Braun that we're finding that in a mini-halo of 10 to the 6, a single per-instability supernova can completely disrupt the mini-halo. And so here the key point is that these low-mass ultra-faint dwarf galaxies, if they are mini-halo, they preferentially retain the metals produced by low-energy faint supernovae, and therefore they have a lot of carbon-enhanced stars. And then you can also study the origin of the different groups, and I can come back later to this if you want. Now, what about instead the per-instability supernovae that have been discussed yesterday? I really love per-instability supernovae because in this regime, all the stellar evolution models agree. So all the different groups give us the same yields, and this is something very rare, so the results are very robust. And then the last year, there was this very exciting discovery by Xing, but unfortunately, as we heard, that was not really the case. By the way, they were claiming to have found a second-generation stars imprinted by a very massive per-instability supernova. So with Joanna Cuzzurito, one of my postdocs, we used this model, Nefertiti, in order to understand what the implications of this discovery are in terms of initial mass function of the first POP3 stars. So we essentially used two observations. The fact that we observed one star that was supposed to be predominantly imprinted by per-instability supernovae at iron abundance of -2, and the fact that no descendants mono-enriched by per-instability supernovae were found below -2.5 in iron. And so we use this model. There are so many semi-analytical models for the formation of the Milky Way, but this one is designed in order really to study the initial mass function of the first stars and the unknown related to the first stars. So what we did was to assume an initial mass function of this form, so a Larson type, and to vary the exponents and the peak, the characteristic mass, in all the different possible range. And then to understand what this model is telling us in terms of number of per-instability supernova descendants that we do expect in the galactic halo. And then we compared this with the non-detection and with the unique detection. And what we found was this. So I was really impressed by this plot. I'm really proud of that, unless now we can only use a part of it. So essentially here I'm showing the slope of the POP3 AMF with respect to the peak of the POP3 AMF. And what we are showing here is that the non-detection of per-instability supernova descendants at iron abundance lower than -2.5, you will have many stars with the entire abundance pattern, can allow us to exclude at the more than 90% confidence level the flattest and the top heaviest IMF, okay? And here is the 75% confidence level. So you can see that we already have other constraints on the POP3 IMF. So don't use, please, a flat IMF. It's excluded by the non-detection of per-instability supernova. And then the other part was linked to the unique detection of this, which unfortunately now is not valid anymore. But I still think that this was a very good exercise because it's telling us what are, let's say, the potentialities of these per-instability supernova descendants. So I think we should really look hard and try to find them. Now, then where we have to look in order to find these per-instability supernova descendants? We cannot look in ultra-faint dwarf galaxies because we said that the metals from per-instability are ejected. So we can look in more massive systems, and an idea is in more massive dwarf spheroidal, like Fornax, for example. And there are now ongoing surveys such as for dwarfs that will tell us if this is the case, or in the bulge, as has been discussed yesterday by Kate. And there are, again, searches for that. But an alternative is also to look into the gas, okay? If these metals are ejected by mini-halos, by the progenitors of ultra-faint dwarf galaxies at high redshift, then we should be able, perhaps, to find them in the gas. And so the idea is that we can look at more distant gas clouds and search for the chemical signature of the POP3 stars by doing spectroscopy and then recovering the chemical abundances. Now, I took this picture from Michele Fumagalli that is showing what is the observed metallicity range of different environments with increasing number density. And historically, the kind of absorbers that have been studied the most are the so-called damped Lyman alpha systems, which are believed to be associated to the ISM of more distant galaxies. And more than 10 years ago, there was a discovery by Cook and Maddow of one of these damped Lyman alpha systems that seems to be carbon enhanced, so imprinted by the first supernovae. But then, unfortunately, some years later, then this observation was not confirmed. So what we have in this plot, in which I'm showing the absolute carbon with respect to the iron abundance, is that the DLAs are all in this part of the plot, and here the low carbon band is what Alex G was presenting yesterday, is where essentially these carbon enhanced metal poor stars imprinted by the first supernovae resides, okay? And so we can ask why we don't observe the signature of the first stars in these more distant DLAs. And probably the answer is that the gas is so dense that after the formation and ejection of metals from the first supernovae, then the star formation can restart, and we can just produce POP2 stars. And as you saw in the very simple model, even a 10% contribution from POP2 stars can really slow down the carbon over iron abundances. So it was washing out the signature from the first supernovae. And then an idea can be instead to look for more diffuse absorbers, the so-called Lyman limit systems, or the sub-DLAs, in which instead the gas remain too diffuse to be able to form stars. So somehow it's quenched, the star formation, and then we can still look at the imprint of the very first stars. So with this idea in mind, with a master student at that time, Andrea Saccardi, and in collaboration with Valentina, we look at the X-shooter spectra of 30 Lyman limit systems. Actually, Andrea and Valentina performed the analysis, and the results for the very metal poor absorbers are shown here. So they are the yellow and the red points in this diagram, while the black dots are the abundances of the stars in the galactic halo, and the cyan are the abundances of the stars in ultra-faint dwarf galaxies. So what is really surprising me is that, as you can see, these absorbers, so this is gas at high redshift, let's say redshift 3-4, and these are stars in the present-day universe. So we are comparing apples and pears, but you can see that they follow roughly the same trend. And then we plot again the same in the absolute carbon abundance, and you can see that these three red points are residing in this low carbon band. And actually, we only have upper limit for iron, so it can be even going in that direction. So this means that by looking at this more diffuse absorber, we were able to find the chemical signature of the first supernovae. And these objects are consistent for being predominantly imprinted by these low energy faint supernovae. So somehow we are finding the high redshift gaseous analog of CMP North stars. Now, what about per instability supernovae? Well, almost 1 year ago, no, 6 months ago, there was this paper coming out from Christensen and collaborators showing observations of absorbers at high redshift with the James Webb, and the points are this magenta, that in this phase, the silicon over oxygen with respect to the carbon over oxygen, which was proposed by Umberto Maio and Benedetta to be a good diagnostic to find per instability supernova imprints, are indeed consistent with an imprint from per instability supernova. So these are the prediction for the per instability supernova. Now, I use this plot that is from our own model. So here, the red is 100% imprint from per instability supernovae, and the shaded region is predominantly imprint. So 50% at least of their metals are coming from per instability supernovae. And you can see that there are 3 objects which are consistent with this scenario. So we were very excited. And again, we did this in collaboration with Valentina, and Valentina realized that actually some of these objects had public available X-shooter spectra into the archive. So she reduced them. The resolution is much higher, and unfortunately, for all the data, what we have is that the silicon over iron and carbon over iron abundances change. So at the end, there is just, at the moment, one absorber that is still consistent for being imprinted by per instability, and for this, we don't have the high resolution spectrum. Now the figure here is a bit more complicated. What I'm overplotting here is also the imprint predicted for other population 3 supernovae in blue, and predominantly imprinted by population 3 supernovae. And what we call the confusion region is this gray area here. And here we show instead when we have a predominantly imprint by normal population 2 stars. So what you can see is that all the points now are more similar to the one that have been already observed and accumulated in the literature, and they are consistent with this confusion region. And essentially, in the confusion region, we don't know what has been the main pollutant. It can either be POP2 or POP3, okay? So there is ambiguity. So what is needed are more chemical abundance elements. We cannot do anything just with 3 elements, okay? And then, again, it was still an important work, because then we developed diagnostics in order to find this chemical imprint from per instability supernovae, and I'm just showing 4 of them. And as you can see, there are some elements, for example, the low aluminum over magnesium or the very high silicon over oxygen, that are the key in order to find this per instability supernova signature. Okay, so I think that with future observations, and especially with Anders from the ERT, we really have the possibility to find them if they exist. Okay, now in the last 3 minutes, and with this diagnostic, we were actually able to identify an object in the Saccardi sample, which is still consistent with an imprint from per instability and another POP3, but in this case, per instability can only account for 10% of the metals. So again, is really a minor contribution. So at the moment, we are lacking the imprint of this per instability supernovae. Now, let's flash on to what we see at higher redshift. So this is a plot from De Genio and collaborators, and in this case, they are measuring carbon over oxygen and oxygen in emission lines, okay? And they are comparing with DLAs, Laman limit system stars in the local universe, and the points are these red ones. And they also make comparison with the yields of POP2 supernovae and with our model, Varney et al. In green. And again, it seems that what they are finding, this IC over oxygen at this oxygen abundance, is consistent with an enrichment with low energy POP3 supernovae. And finally, roughly a month ago, Andrea showed me that there was this paper coming out in which they actually measured the oxygen over iron abundance in Gianzar 11, and this is the point shown here. And actually, if you look at the diagnostic, if you have this oxygen over iron, well, you may be also consistent with per instability supernovae, but also with other different sources. And then they also measure the neon over iron abundances. And in their work, they are showing this figure here. So here is overplotted the prediction for per instability supernovae, and here there are some other sources, and I guess the yields are from the Japanese group. So they were claiming that perhaps they are observing the per instability supernova signature at very high redshift in these galaxies. I did the check with our model, and again, here where the arrow is going is also in the confusion region, so I'm not totally convinced that what we are observing is really a signature of per instability supernovae. So, to conclude, I show that the chemical fingerprints of this massive per instability supernovae is missing. Is missing in present-day stars, in distant gas clouds, and in high redshift galaxies. According to me, there is not an indication. So why is like that? I think we have a serious problem, because we saw yesterday that theory is predicting that the first star should also be so massive. So perhaps we do not understand something, and it is very important to find them, because even the detection of a single star imprinted by per instability supernovae can give us very tight constraints on the IMF of the first stars. And then instead, we saw that the chemical fingerprints of low energy POP3 supernovae have been found in many of these carbon-enhanced stars, and also in this absorber at higher redshift. So one can also wonder, so what's the nature of this absorber? And perhaps the scenario is something like that this absorber, this is something similar to something we proposed with Andrea in 2012, these absorbers are perhaps just mini halos that form their POP3 stars, and then the formation of subsequent generation stars were quenched because of the UV background. So they were not photoevaporated because they have metals inside the gas, but they were not enough dense in order to produce further star formation. I don't know. Clearly, if this is the case, then it means that, okay, there is less hope to find directly POP3 stars. Alternatively, this absorber that we are seeing at redshift 4 can also have been imprinted by a recent event of POP3 supernovae, because we saw that simulations are showing that POP3 stars can still persist down to redshift 4. And clearly, if this is the case, then it would be a good news, because then we can at least use James Webb, look at lower redshift, and try to find direct detection of POP3 galaxies. That is also something that is still missing. And I stop here. Thank you.
Thanks for the nice talk. So, questions? Yes, Priya.
Very nice talk. Sorry. Yeah. Very nice talk. I was curious that, in the ultra-faint dwarfs in CDM, that they have kind of very quiet emerging histories. So with the abundance measurements that we have, can we put a constraint on the number of episodes of star formation that have occurred?
Oh, in principle, I think so. So the ultra-faint dwarf galaxy that we are studying here in very much detail is the so-called ultra-faint dwarf galaxies Bootes-1, and we choose Bootes-1 because it's the best studied system. And what we are finding, actually, okay, is that in this case there are no mergers, and essentially the main burst of star formation lasts 100 million years only. So in 100 million years, you are already able, I'm trying to see if I can find that, you are already able to produce all these stars that you see today, yes. So this is roughly what we are finding, yeah. So, yeah, even less. Well, this is just one realization, then we have more. Some of them are more prolongated, so, yeah.
Other questions? Yeah.
So thank you, Stefania. I was curious to know if what is the adopted energy distribution function for POP2 stars, and how this may affect, so suppose that you continue to have faint supernovae even in POP2 stellar generations, how this would complicate the scenario.
Okay, so I have a study on that. I didn't have the time to show, so good that you're asking me this. So essentially, what we did in a previous work was really to use this energy distribution function as a free parameter. So we were really varying this energy distribution function. We parameterized, if it's coming back, with this EL minus alpha. So I alpha means that we predominantly have faint supernovae, and low alpha that we have more or less the same amount of hypernovae and faint supernovae. And then we tried to study to see if it was possible, sorry again, I should come back because there are hidden slides, to break this degeneracy, to study simultaneously the initial mass function of the first stars and the energy distribution function. So what I'm showing here is the comparison for two different POP3 IMF, characteristic mass 1 and 10, and the colors show different energy distribution functions. So the red is more hypernovae, and the blue is 100% faint. So what you can see is that with the metallicity distribution function, you cannot disentangle, not at all. You can do a bit better with the fraction of carbon-enhanced stars. So essentially, we are able to rule out the models with too many hypernovae. So the flat, almost flat, and two more hypernovae can be excluded, that are the one here, even if the errors are quite big. But there is a degeneracy. So this means that models with different POP3 AMF and different energy distribution function, couples of this can equally well reproduce the data. Sorry, for POP2 stars, I understood the energy distribution function. So for POP2 stars is the Larson IMF. We are not varying that. Sorry, I misunderstood.
Which assumes that even for POP2 stars, you can have faint supernovae. How your inference would be affected?
Okay, this can clearly affect a bit, even if we did this calculation. So we tried to use the Japanese yield from faint supernovae, and without POP3 supernovae, faint POP3 supernovae, we cannot reach the very high carbon of Orion. So the scenario is still the same. Clearly, let's say, they can help in order to produce more carbon, but it's not changing the results. Yeah.
Hi, thanks so much, Stefania. That was fantastic. I have a question about, so I think we can argue about the star formation duration for ultra-faint dwarfs, which I think is actually much longer. But at least in the different gas systems, I think the times and redshifts are like far and beyond where you would expect type 1a supernova to be contributing. And a lot of the diagnostics, I think, are, like silicon and iron and that sort of thing are, there's a, at least a 50% or higher contribution from those. So I'm wondering about how important that might be for some of these signatures and contaminations and that sort of thing.
Okay, so we had a look also at the, and perhaps in the paper there are also, so at the yields of supernova 1a, so every time we find an interesting object, we also consider that. And now with Irene Vanni, we are producing an online tool that can be used, that will be for the public, in which you can really select what you want to do, and you can have your results. So we always look at the supernova 1a, but the key point, let's say here, so we look at the supernova 1a and also the direction in which dust can affect the results, which is also an important part, because for some of these absorbers, we don't know what is the metallicity, so this can also be important. So for the Saffardi results, this is not affecting our finding, also because they have a relatively low iron abundance. So if you consider also the contribution for supernova 1a, then they will jump at much higher, here they are, at much higher iron abundance. So you can see here we have just an upper limit for iron. Here you can see it better. They are here, so they are below minus 2.4. So let's say if you consider supernova 1a, so we did this calculation, then we will jump, you expect to jump at higher iron abundances, so not to be more in this regime of very metal poor system. I don't know if I addressed your question. Okay.
Yes.
Thanks for a nice talk. So this might be a naive question, but you were arguing that the Lyman limit systems are sort of more likely to show the signatures of carbon enhancement and be more like the ultra-faint dwarfs versus the DLAs. And I'm just naively, I guess, it feels like metallicity should be the whole story. You were saying that density matters, but I was just wondering, I didn't quite follow why.
Okay, so the key point here is that you need to suppress the subsequent star formation in order to have the POP3 signature, okay? So you are looking at the gas. If the gas, and you're at redshift 3, 4, okay? The first stars are expected to form at much higher redshift, okay? So there are two scenarios. Or you are looking at pockets of gas, perhaps the circumgalactic medium, I don't know, which has been recently imprinted by POP3 supernovae. So this means that we can use, if you want, these absorbers are signposts in order to find POP3 galaxies. This is an idea. Or the star formation of POP3 and the injection of metals from POP3 supernovae happen at much earlier time. But in that case, you need to suppress the star formation, okay? Because if you then form subsequent generation of POP2 stars, that they can rapidly enrich, they will disappear as supernovae, and so they will enrich the medium and they will change, and the signature of the POP3 will disappear, okay? So I was suggesting that perhaps they are mini halos, because what is really surprising me is the fact that we are finding so astonishing similar results. Also, for example, here we are comparing the metallicity distribution function of the absorbers, that is the violet, with the metallicity distribution function of stars in ultra-faint dwarf galaxies.
Yeah, so that's what I don't get is why is metallicity not the whole story? Like, isn't metallicity just a good proxy for past star formation and contamination? Why does it have to be density as well? That's the part I didn't quite follow.
Because the density can tell you if you're able to form stars or not.
Yeah, but DLAs and LLSs are at nowhere near, I think you're saying they're closer to the galaxy maybe? You're saying the densities are not star formation.
I think we don't know what they are, to be honest. So this is my point. So I think it will be very interesting to understand what these objects are. I don't have an answer. I propose two possible scenarios, but we don't know what they are. Perhaps they're just, as you said, pockets of gas close by a galaxy that is forming POP3. But if this is the case, then it means that there are POP3 galaxies at redshift 4. So James Webb should be able to catch them. And if we don't find them, then there's something else.
Thanks.